Wave characteristics, basically vocabulary about the wave, right? First, in 3 dimensions, the wave looks like this, right? The wave is moving to the right. The problem with this description in 3 dimensions is that if you look from top and bottom, right, you can't really see the difference. So what we did is we take the important parts, right? And this important part is going to be the peak only. So in red, I'm going to put a line on the peak. As long as we know where this peak is, you have a very good idea what it's going to look like, even if you look at it from top and bottom. And if you want to draw it, you only draw these peaks. Everything else is implied, right? So we will call this peak the wave fronts. So this is the biggest part of the wave, right? And the distance between these wave fronts is the wavelength. So, but if you just look at this in 3, from top to bottom, you would see just 3 lines. 1, 2, 3 lines, because there's 3 waves. Well, you know where the waves are now, right? The peaks are in these lines, but you have to also know where they're going, so you need what you call a ray, the direction they're moving, basically the velocity. So there is the wave fronts, which are these. The only thing we draw from a wave, and there is the wave ray, or the velocity direction, right? Which is important. We should know where it's going. So, next part. There's different types of waves. And these waves over here just look like walls, right? They don't become any bigger, they don't become any smaller. So these are 2-dimensional. If you make the disturbance 1-dimensional, there's going to be a line, let's put this in red, that goes across this. And this line is what's making the waves go in cylinders around it, right? So the wave front is a circle, but it's a cylinder in 3 dimensions. And this is when, let's say you put a stick in the water and you move the stick up and down, it will make cylinders, right? And how is it different from what we normally see? Well, the third type of wave would be a sphere, right? Like sound wave. If I click if I snap my fingers, right? The sound goes in every direction in a sphere, right? Normally, we're gonna just use this version, right? The other 2 have different equations for the amplitude, intensity, and energies, but this is usually what you have, right? Most of the times, the waves come from a center. Like a light bulb, the light comes from the center, right? And it expands in all directions. Right. Next is amplitude and intensity. And this was part also of the questions in the homework. So this explains most of what you saw there. Just as an aside, the questions are also there just in case you can think further, right? If you can, it's great. It's a challenging question. If you cannot, well, we learn it today. So first, we're gonna define intensity here. And you have to listen carefully because previously we had only defined power, right? We defined power as equal to the work divided by the time. So what is intensity? Intensity is defined as the power per area. And there's going to be units for this, right? The units for intensity are watts per meter squared. So why do we need this, right? Why is there even an area underneath this? Like, why can't you just use power? Well, let's go back to this example we had here. Let's say there's a source. This source is using energy to make waves, right? And as it makes waves, they expand and they become bigger. So let's say it uses, the frequency is 1, basically. Let's make this example, frequency equals 1 hertz. So there's 1 wave per second. And let's make the power 10 watts. So it's 10 joules per second. So basically what this means is every wave has 10 joules of energy, right? So I'll put right next to it, therefore, every wave has 10 joules of energy. But that energy becomes thinner and thinner as the sphere gets bigger and bigger, right? Does that make sense? If it's really close together, you can get a little bit of area and there's a lot of this 10 joules of energy there. But if I go further away, the energy becomes thinner and thinner, it gets less and less energy per unit area of wave, right? And this is why we use intensity. Because if you use power, the power is the energy when it was in the center, right? If you go further and further away, you need to know how much area you're getting because you don't get all of this energy, right? You just get a fraction. And the fraction depends on the area you have and how far you are, right? AKA the intensity. This is not important. So, first, the area of the sphere depends on the distance, right? So let's say area, what's the area of a sphere? Pi r squared, right? Because it's the surface area only, we don't count the volume. And you have this, and r is the radius. So if you have a bigger r, you have more area, or have the square of the area, right? So if you double the radius, the area is 4 times as much. But remember, all this energy is evenly distributed along the surface, right? So we have the intensity is equal to the power divided by the area, right? Let's say if I double the distance, area quadruples, right? Becomes 4 times as big. So the 0 represents the initial. So the new radius or the distance is twice as big. Therefore the area, new area is 4 times as big as the initial one. And that means if let's put these numbers inside, we're going to find the new intensity. So I'm going to write these in terms of the initial ones. And I'll write a new equation for the new intensity. The power stays the same source. But the area is 4 times as big. This means the intensity is 1/4 of the original intensity. Because this power divided by the initial intensity was this. I just replaced this with I0, right? And this is what we say intensity is not proportional to the amplitude, it's inversely proportional to the square of the amplitude, right? So we can add inversely. Proportional to amplitude squared. Sorry. Inversely proportional not to the amplitude, to the distance squared. Right? We haven't talked about the amplitude yet. What about the amplitude though? Right? And this is what we talked about in the problem as well. We know how the energy and intensity is going to change, right? It evenly spreads out. But what about the amplitude? Let's get additional places here. And this is the area, so I'm gonna use another letter for amplitude. I'll just write the whole word amplitude so you don't get confused, right? Let's put amplitude equal to, let's say x0, right? Or the maximum displacement. This means that if the amplitude changes, we know that the energy changes, right? And again, the equation for the potential energy stored in an oscillating object is going to be 1/2 kx squared, right? But this is for just one object. But remember, the waves are just a whole collection of a lot of objects, right? Infinite number of points. But this still holds up, right? It just depends on the amplitude. How big is this amplitude, right? So the amount of energy is proportional to the amplitude squared. Therefore, power is proportional to energy, right? Or work. Therefore, power is also proportional to the, this should be amplitude, right? That's what we agreed on. And intensity is also proportional to power, so intensity is also proportional to the amplitude squared. Right? And this brings us to a very unorthodox conclusion. This is what we actually need, right? I'm going to write this down. Intensity is proportional to amplitude squared. And I'm going to zoom out so I can write everything here. Squared. And intensity is proportional to the amplitude squared. The intensity is inversely proportional to the distance squared, right? So what is the relationship in distance and amplitude? Well, they're just inversely proportional, no squared between them. So amplitude should be inversely proportional to the distance. According to this, as long as it's a spherical wave, right, starting at one point. If you have a rod, it has a cylinder, not exactly the same equation, right? You have to use the equation for a cylinder, not a sphere. Last thing about this, we're going to highlight the important part. Just a second. In yellow, which is what's going to allow us to answer the questions, right? This doesn't come up very often.